I think in video 69 we first started talking about phasors, and we want to review just some of those basic concepts and then see how to solve some specific phasor problems. And I think in video 69 we had this kind of a situation where we had a circle of reference and it had a radius vector, say of magnitude A, and then the radius vector sweeps about the circle with an angular velocity omega. That's measured in radians per second, and again we discussed that in video 69. And then we could imagine the vector being at, say, 90 degrees, changing position, going like this. And as it sweeps around the circle, we can also see how this could be representative of a sine wave. Because here, let's just say that the height on this graph will be the vertical component of the vector. So if the vector is right here, the height on the graph for this corresponding position would be that same height. So if we start at t equals 0, the height is 0. Then when we're here at 90 degrees, or pi over 2 radians, then the height is going to be a. Then here it goes back to 0 again. Then it's minus a. Then it's going to be 0 again. So it would look something like this. Where this would be a times the sine of omega t. And this is a and that's minus a. So it starts off, the vector is here, the height is 0, then it rotates up to here, now the height is a, that corresponds to this, then now it's going to be decreasing again until it's 0, then it sweeps out towards minus a, that's this part of the graph, then it goes back to 0, that's this part of the graph. So we see how a phasor, and a rotating vector like this is called a phasor. So this would be like a phasor representation of a sine wave. And we could also use a phasor to designate a cosine wave. In that situation, instead of starting here, we can start at t equals 0. It's up here. And again, has a magnitude of a, and it sweeps around the circle counterclockwise at an angular velocity omega. So now the corresponding graph looks something like this. This is t, and this would be a times the cosine of omega t. At t equals 0, the height here is a. That's what that is. And then it goes to here. The height was a, now the height is 0. That's this point. Then it goes down. That's minus a. That's this point. Then up to here where the height is 0. That's this point. Then up to here, where once again it's at a height of a. That's that point. So our phasor can represent either a sine wave or a cosine wave, depending upon where it is at time t equals 0. If it's right here, then it represents a sine wave. If this is shifted 90 degrees, then as it rotates about the circle, it will represent a cosine wave. And this shouldn't be surprising because we know from trigonometry that the sine of theta plus 90 degrees, or pi over 2 radians. That is the cosine of theta, which again we just kind of demonstrated just here with our simple phasor diagram. So the point is that we can represent information with the phasor diagram, or that same information here as a sinusoidal wave. And here, this is usually called the time domain, and this is called the frequency domain. Now, in the frequency domain, or the phasor domain, usually what the relevant information is the magnitude of the phasor, or the circle radius vector, and the phase angle. Suppose we have it like this, where here we have a radius vector, vector A, of magnitude A. At time t equals 0, it's perfectly horizontal. Then we have a second one, obviously the same magnitude, but this one gets a head start. This one is up at, as it starts with a phase angle of, we'll just call it theta. So this, that would be A times the sine of omega t. But for this vector, where at time t equals 0, it's already pointing up here, then that would be A times the sine of omega t plus theta. And graphically, it might look something like this. Here is the sine of omega t, and here's the sine of omega t plus theta. Of course, it's the same shape, it's just shifted. Same thing in our phasor diagram. The vectors are the same shape, they're just shifted an angle of theta apart from each other, and they're both going about the circle with the same angular velocity, so this angle theta between them is always going to remain the same. Now, we showed these here as in a circle, so they would have to be, these radius vectors obviously have to have the same magnitude, but the problem doesn't have to be set up that way. We could have it something like this. Say we had 5 times the sine of omega t plus 30 degrees. And we had another one that was, say, 6 times the sine of omega t plus 60 degrees. Now notice before we said omegas in radians, so it's an angular velocity of radians per second, so multiplied by the time. This gives us an angle measured in radians. Here we're talking degrees. Of course, we can always convert radians to degrees if we want to. But actually, we'll see that this part isn't important. It's these phase angles that we pay attention to when we're considering the phasor diagram. So, for example, for this one, we could say, well, here's the horizontal line, and for this one it makes an angle of 30 degrees and has a magnitude of 5. And this one has a magnitude of 6 and a phase angle of 60 degrees. Like this. So in the phasor diagram, we're concerned about 2 parameters: the magnitude of the vector and its phase angle. And that's all. But this, considering the problem like this, has the same information involved as considering the problem like this. For example, Suppose you wanted to add these together so that we have this plus this. That's going to equal something, we don't know what it is, times the sine of omega t plus some phase angle. We don't know what that phase angle is. So there's two unknowns to be determined. If we add these sinusoidal waves together, what will be the amplitude of the new one and what will be the phase angle? Well, we can figure this out a lot easier actually from the Phasor diagram. Let's consider it like this. With an x and y axis. So we have this one, magnitude 5, angle 30 degrees, and we have this one, magnitude 6, and a phase angle of 60 degrees. So let's call this vector v1 and this vector v2. How can we add those vectors together? And of course, this is the y-axis and this is the x-axis. So we want to add these together. We want to add vector v1 and vector v2 together. To give a new vector v3. And the magnitude of this new vector v3, that's going to be that. And then this vector v3, of course, it's going to have a y component and an x component to it. And then the phase angle that it makes, that will be the inverse tangent of the y component of v3 divided by the x component of v3. So we will know what this is, and we know what this is just by working with our simple Phasor diagram. Before we do, let's try and make this a little bit neater. Things got kind of crowded together here. So our situation is something like this. Thinking of it now on the x and y axis, here we have this phasor, magnitude of 5, angle of 30 degrees. And then we have this one, magnitude of 6, angle 60 degrees. $60 for that one, 30 degrees for this one. This has a magnitude of 5. We're calling this V1. We're calling that V2. We want to add V1 and V2 together. And we first consider problems like this in video 71. Of course, we know it's not difficult. This will give us a new vector, V3. And that will have an x component and a y component. And the y component of this is real easy to find. It's just the x component and the y component. Let's take the x component. That'll be the x component of v1 plus the x component of v2. So for the x component, that's 5 times the cosine of 30 degrees. This horizontal distance is the hypotenuse 5 times the cosine of the angle 30 degrees. So we have 5 cosine 30 degrees plus 6 times the cosine of 60 degrees for this one. So add these two x components together, and we'll have the x component of our added vector. And this is the square root of 3 over 2. Well, that's like 0.866. we multiply it by 5, and we get 4.33. The cosine of 60 degrees is 1/2, so that's 3. So this equals 7.33. So the x component from adding these together is this. Now let's get the y component for V3. So we have, to get the vertical here, that's going to be 5 times the sine of 30 degrees. Plus, here we're going to have 6 times the sine of 60 degrees to get that vertical component. And this, the sine of 30 degrees, is 1/2 times 5, that's 2.5. This is the square root of 3 over 2 times 6. That'll be 3 times the square root of 3. I think that's like 5.2. This gives us 2.5. That's 1/2. This is the square root of 3 over 2. 6 times the square root of 3 over 2, or 3 times the square root of 3. We get 5.2 for that. So the y component is 7.7. So for our new vector V3, and Vx is 7.3, Vy is 7.7. What's the magnitude of it? So that will equal the magnitude of V3. That will equal the square root of this squared plus this squared. For this we get 53.7. And that squared we get 59.3. And then add these together and take the square root. And this is like the square root of 113. That's like 10.63. So going back to our diagram then, adding this vector plus this vector gives us another vector. Its magnitude is 10.63. Now we need to know what angle does it make with the x-axis. That's going to be its phase angle. So let's make some room. We know its magnitude, that's 10.63. Oops, can't erase yet. Y is 7.7. Vy equals 7.7. Vx equals 7.3. Okay, now, in the magnitude, that was 10.63. Now we need to know what is the phase angle. So the angle that our new vector V3 makes with the x-axis, that will be the inverse tangent of Vy 7.7 divided by Vx. And that's the inverse tangent. I think it's just a little bit over 1.0 something. And we looked that up in a table of values, and that's approximately 46 degrees. So when we add vectors V1, this has a magnitude of 5. It makes an angle of 30 degrees. V2 has a magnitude of 6. it has an angle of 60 degrees. We add them together, we get, this is going to look kind of messy I suppose, a vector magnitude 10.63, and that makes an angle of about 46 degrees with the x-axis. So that means here this is 10.63, and that angle theta, that phase angle, is 46 degrees, what it makes with the x-axis. So and there it is. So this sine function plus this sine function, we can add them together and get this sine function. As you can see, it's much easier to do when you use the Phasor approach. We could have graphed each of these out and then added them together graphically, but that would take a long time to do, much quicker and much easier to do using the Phasor representation.